So welcome, this is 48K tape 1, and we're going to start off a new section now talking about linear momentum and also collisions. We divide this chapter up into 3 bits. We divide it up into a first bit which is talking about linear momentum, which is new to most of us, force, and also another new term, impulse. And then we use those ideas to look at the collisions of particles. This is in contrast with the last bit, which is largely to do with the next chapter. So we have these first 2 bits which go hand in hand, and then we have the third bit which is for the last chapter, for the next chapter. If I look at this section, we start off with the definition of momentum, and we say momentum equals mass times velocity. Momentum is a vector, and so is velocity. So wherever the velocity points, the momentum will be pointing. They won't be the same size necessarily, but they'll be in the same direction. Momentum's a weird thing. You wouldn't necessarily observe it. If I look at a car moving, I see its velocity, I see its speed, I see its acceleration, I see its position. I don't necessarily see its momentum. The momentum is the product of its mass times its velocity. So if I take a small mass and multiply it by a big velocity, let's say a small car going really fast, that has the same momentum as a big mass going at a small velocity. Let's say a bus rolling slowly along the road. I don't know about you, but I don't think of those two as been the same thing. So it's a strange situation, but the trick is that from the beginning to the end of a collision between objects, speed is not maintained, and neither is kinetic energy for the most part. Sometimes it is, but they're rare examples. The only thing that actually is maintained all the time is this thing called momentum, and that's where its utility comes in, and that's why we use it so much. So then we turn our attention to linking momentum to force, and what we remember is that acceleration is the rate of change of velocity. So A is equal to delta V by delta t. It's the rate change of velocity in time, which we can write as dV by dt. And so if I say, well, I have this thing called momentum, so dP by dt must equal d by dt of mv, and mass is a constant, so that can come out. So I have m dV by dt, and I recognize that that's acceleration, so I get ma. So dP by dt is like saying ma. So whereas before we said the sum of the forces equals ma, now we can say the sum of the forces equals dP by dt. In fact, if I understand it correctly, Newton never said F equals ma. He thought in terms of dP by dt's. So if I now think in terms of linear momentum and a new idea called impulse, I can define impulse. Impulse is the product of a force and how long it is applied for. So the force and the duration of the force. If I have a big force, a big unbalanced force causes a big unbalanced acceleration. But the question is, how long is that applied for? I mean, the acceleration by itself doesn't tell you everything. So we say that impulse is defined as the integral of f dt. And we can say, well, if I remember that f is equal to dP by dt, I get that the impulse is equal to the integral of, well, not f, but dP by dt dt. And so I get the integral dP. So I can say that the impulse, this new idea, is equal to the change in momentum. And there's an issue. If impulse is equal to change in momentum and the sum of the forces equals dP by dt, these are sufficiently new ideas and they involve similar symbols or similar parameters, it's very easy to get them confused. So be very careful when you learn these I would learn them side by side, and I would say this is impulse and that's force with momentum, and just make sure you don't get them confused, because I do see that from time to time. 3 ideas basically, I guess. Momentum and force, and then impulse and momentum, maybe 4 ideas. Let's do some examples. So what is the momentum of a 3 kilogram block traveling at 4 meters per second in a negative direction? So negative and positive. There's my positive end, there's my negative end. I'm on a road, I have a 3 kilogram block, and I'm traveling at v equals minus 4 meters per second. I got to take the direction into account, so that negative sign is important. I say what is the momentum? P equals mv. Well, really it's vector momentum is equal to mass times vector force. So P is equal to, it's going to be 3 times minus 4, the negative sign giving it direction, which equals minus 12, and the units, kilograms meters per second. Sometimes with the number line we tend to forget that it's a vector, but it's a vector. It's going in the positive direction as opposed to the negative direction. That's a magnitude, and a direction gives you a vector. Let's talk about it in terms of 3-dimensional stuff. So here's a 5 kilogram block, and it's got some velocity, and the velocity is 3I plus 2j minus 4k meters per second. There's my velocity. Here's my mass. It says, what is the momentum of a 5 kilogram block that has a velocity of 3I plus 2j minus 4k? And again, I say, well, you know, vector momentum equals mass times vector velocity. So vector momentum is equal to, well, this would be 5 times 3I plus 2j minus 4k. So vector momentum is equal to 15I plus 10j minus 20k. And that's going to be in kilograms meters per second. Don't forget your units when you're doing an IJK calculation. Let's look at another one. So now we have 18 Newton forces applied to a particle. So this is 18 newtons. Oh, the force acts in the positive x direction. That was lucky. The particle is initially at rest. Vi is equal to 0 meters per second. What is the momentum of the particle at time t equals 6 seconds? So here's the particle. Delta t equals 6 seconds. And I want to know what the momentum of the particle is. So this is my momentum, my p. And let's have a look. I know that F is equal to dp by dt, which equals, well, if I assume a steady force, delta p by delta t, and my delta p would be p final minus p initial over delta t. So I can say, 18 positive is equal to p final minus, let's look, yes, p is equal to mv if the initial velocity equals 0, the initial momentum equals 0. So my initial momentum is 0. It's never mentioned, but it's clear from the visualization, over my time interval, which is 6 seconds. So that gives me that my P final is equal to plus 18 times 6. 6 eighths, 48, carry 4. 6 ones are 6 and 4 makes 10. And that would be, again, kilograms meters per second. 108 kilograms meters per second. If I do the same thing now with IJK, so here I have a particle, and I have a force, 3I plus 2J plus 4K newtons. There's my force. And the particle has initial momentum, so here's the initial momentum, P. And this would be 1I minus 6J plus 7K kilogram meters per second. They're not in line with each other. They don't have to be. They could be, but the momentum always lines up with your velocity, but it doesn't line up necessarily with your force. This thing is a particle. It has a velocity in a certain direction, and now I'm applying a force to it. That force is going to cause the trajectory of the particle to change, and in doing so it's going to change the velocity. So I'm going to get a V final, and I'll also get a P final, of course, because P final is just the mass times the V final. What is the momentum of the particle at the end? Okay, so what do I know? I know my force, I know my P initial, and I want my P final, and I know the time interval. It says delta t equals 5 seconds, delta t. So again I can say, oh yeah, well, the force is equal to dp by dt, which equals, if everything goes steadily, it's delta p by delta t, which equals P final minus P initial over delta t. Let's rearrange this a bit more completely, because I'm going to be working with IJKs. I want to know the momentum of the particle at that, so I want to know my final momentum. So P final is equal to F delta t. I took the delta t and multiplied it into the F, and then I got to add on P initial. Now that's what they call in English literature foreshadowing. That's something that's coming up, but we won't mention it at the minute. So we go, I need to do a sum. I need to go IJK, and the first thing I need is F delta t. So I'm looking and I'm saying, well, I want that force, and it's got to be changed by the delta t, of course, is 5 seconds. So it's going to be 5 times 3 is 15, and 5 times 2 is 10, and 5 times 4 is 20. And then according to my equation, the next thing I need is P initial. And P initial is not 0 this time. It's 1, and it's minus 6, and it's plus 7. And according to this math, I add these two guys together. So I say this is going to be 16i plus 4j plus 20, and 7 is 27k. And it's going to be a momentum, so it's kilograms meters per second. Okay, that's not bad then. Okay, let's look at the next bit. Particle is acted on by a 12 Newton force that acts in a negative direction. Here I'm back on a number line, positive end, negative end. This is going to be minus 12 newtons. Acts for delta t equals 5 seconds. It's continuously acting for 5 seconds. And what's the impulse? Also, now we're introducing impulse. Impulse is equal to force times the delta t. So this equals minus 12. It's a vector, so the sign's important, times 5, which equals minus 60 Newton seconds. Okay. And then let's have a look at this next one, which is in IJK. So here's my particle, and here's my force. 3I plus 2J plus 4K newtons. There's my force. And it acts for 4 seconds, delta T. So I can say, oh, I is equal to F times delta T, which equals, it's going to be 3I plus 2J plus 4K times 4. So I is going to equal 12I plus 8J plus 16K Newton seconds. Okay. Next bit. Now we're going to bring it together. And we say, this next question says a stationary particle is acted on by a 7 Newton force that acts in the negative direction. Minus 7 newtons. Negative and positive, that means there's a positive end and a negative end of a straight line situation. Force acts for 3 seconds. Delta T equals 3 seconds. And what's going to happen? This is going to go over to this side, and it's going to have a different velocity, different momentum. What is the particle's momentum? So I want P final. Over here, V initial equals 0 meters per second. So P initial equals 0 kilogram meters per second. I want to find this P final. Okay, so I actually know that impulse is equal to force times my duration, and I also know that impulse is equal to my change in momentum. Those are the two equations that come to my mind quite readily. And so if I put these guys together, I know that my force times my duration is equal to my change in momentum, which equals P final minus P initial. So I look and I say, well, minus 7 times 3 is equal to P final minus my change in my initial momentum, which is 0. 0 velocity means 0 momentum. So my P final is equal to minus 21, and it's going to be kilograms meters per second. So here I'm bringing those two things together to solve a problem. Just by the by, I'm basically saying that Newton seconds is equal to a change in momentum, and the change in momentum is kilograms meters per second. It's important to realize that equations have the same numerical values, but they also have to have the same dimensional values. But they don't always show this by the same units. So these two sets of units are dimensionally the same, and it's not obvious. And so I can show it to you by saying, well, Newton seconds, that's a bit like kilograms, well, it's exactly like kilograms meters per second times seconds over seconds. So mathematically I've done nothing. But if I look, that's a kilogram meter per second squared, which is a Newton, and that left be a kilogram meter per second squared, which is a Newton, and that leaves behind the second. So can you see how they are the same dimensions? They just don't look it because we're using different units. Just a small point at the end. So there we have it.